Good morning everyone, I am Mr. H. Thank you for joining me for this video where we're looking here at this specific and single question. It's a hard one. We have to solve this differential equation x cubed plus xy square all in a parentheses where the dy dx is equal to 2y cubed. How would you go about solving this? This equation over here and expression is hard simply because the integral part of it will be hard. When you have that, just push everything onto the other side. You're looking at a 2y cube over, in terms of a denominator, x cubed plus xy squared. But when you're looking over here, you might want to be thinking about separation of variables, but it would be hard to separate the x out of here. But what you can do is a substitution, y equals vx, you know that technique. And then in terms of the derivative, you have a dy over dx is equal to, and you know what that is, it's equal to v plus x dv over dx. All of this will come into play over here. Y equals vx will come right here in places of y. You have a dy over dx. Remember, dy over dx is synonymous with y prime. So you could have had this question here with a y prime. It would mean the same thing. Anyhow, that is equal to, you have a 2vx whole cube because y is now being substituted for vx. You have x cubed plus x v square x square. Vx coming right in here. When you clean this out, you have a 2x cube v cube over x cube plus x cube v square. Now you can isolate the x cubes and you'll have a 2x cube v cube over x cube into 1 plus v square. These x cubes will cancel out. So let's clean it out. You have y prime is equal to 2v cube over 1 plus v square. But this y prime is very synonymous with this one right over here, and you know that is equal to v plus x dv over dx. You have seen something like this before. Bring the v onto this side. You're really looking at a 2v cube over 1 plus v square minus v over 1 is equal to x dv over dx. You see, by bringing in this y equals vx substitution, we eliminated the y variable. We made everything in terms of x's and v's, from which then the x could be isolated and you could separate the variables. And we're very close to the point where we'll have the separation of variables. When we solve this out, what will you get? You have a common denominator here of 1 plus v square. You will have a 2v cubed minus v, 1 going into this, 1 plus v square times, is equal to x dv over dx. You'll have to open this up. When you open it up, you have a 2v cube minus v cube over 1 plus v square is equal to x dv over dx. Clean this out here on the top. You're looking at a v cube minus v over 1 plus v square is equal to x dv over dx. Now cross multiply these x's and v's onto the other side. This will go onto the other side. This will come over here. And what will happen, you'll have 1 over x is equal to 1 plus v square over v cube minus v dv over dx. Now everything is separated, x on one side, v's on the other side, and everything is attached to their appropriate derivative forms. But this is now the beginning of our problems because we have to integrate this. This integration over here is a little messy because it's work. It's not a single step procedure, it's going to be work, and that work will come in the form of partial fraction decomposition. Anyhow, what can we do over here? How about I erase this over here and I push it out and we get this into our integral forms. I'll have a 1 over x dx. All of this with regards to dx. You know, the dx's will cancel out. You'll have just that with regards to dv. Now that is the item which has to be integrated, and that integration will occur all over here. What we will do here is on the side, remember this, y equals vx, because it'll come in at the end in terms of v is equal to y over x. But I'm going to erase everything except for this part and we'll work over here. Remember, we're still in the process of solving that differential equation and we've come down to that step. This part right here is easy. I'm going to bring everything over here. I'm going to bring the natural log x out of that. Integral of 1 over x is natural log x plus c. But if I do a substitution, c is equal to natural log a, I can write everything here in terms of a natural log because at the end it will come in handy. So I really have natural log x plus now natural log a is equal to the integral of that v components, the v factors. For that I have to do PFD, partial fraction decomposition. Look right here in the denominator. I have a v cubed minus v, which if you work on it is really v into v squared minus 1, which if you factor out is v minus 1 and v plus 1. I have 3 factors over here, therefore in terms of partial fractions I have a over v plus b over v minus 1 plus c over v plus 1 is equal to what? it's equal to exactly your numerator. But in terms of a proper format, v squared plus 0v plus 1. This has to undergo the partial fraction decomposition. The partial fractions will then undergo their separate integral procedures, which will then attach with everything you see right here after the equal sign. Let's do this. You know a common denominator here is v into v minus 1 and v plus 1. The a component here will go into this, a into v squared minus 1. The b component will go in here, b and v plus 1 times, and the c component will go v and v minus 1. And now you have to work on all of this. And what I can do is just erase the denominator because I don't need it anymore. And I can just work here on the bottom. When I compose all of this, I'm really seeing av squared minus a plus bv squared plus bv plus cv squared minus cv is equal to this right over here. But let me start determining what the linear factors are, or the linear systems which will develop from here. I have, in terms of the quadratic components, I have here a plus b plus c is equal to right here 1. In terms of the linear factors, I have a b minus c is equal to a 0. And then in terms of the constant components, I have a minus a is equal to a 1. I've developed these three systems of linear equations, but they're not hard. If I know minus a is equal to 1, I know a is equal to minus 1. When you bring this minus 1 right over here, you can generate a new equation, b plus c is equal to 2, because minus 1 goes on the other side and becomes a 2. This equation and this equation can be combined together. We have b plus c is equal to 2, and we have b minus c is equal to 0. You know here 2b is equal to 2 and b is equal to 1. And then I know what c is equal to. If b is equal to 1, c is equal to 1. So I know all my three items is minus 1, 1 and 1 in terms of a, b and c. All of that now can come right over here, a, b and c, and I'll bring that into play after cleaning out some of this. I know a is equal to minus 1, so I'm going to bring that in right over here. I'll have a minus 1 over v. I know b is equal to 1, so I'll have a 1 over v minus 1. And then c is equal to 1, I have 1 over v plus 1. But all of this right here represents everything coming out from right here in terms of an integral with respect to dv, and these are easy. We just do step by step. We bring them in, minus natural log v plus natural log v minus 1 plus natural log v plus 1. If you are cognizant of the fact how these are in the terms of the order you see, flip everything around, you'll have natural log v minus 1. And when I mean flip everything around, I really mean rearrange them. Natural log v plus 1, and then finally the negative component, natural log v. I've just rewritten everything positive and then minus. And utilizing all of this, it will come over here, and I'll do that. Natural log v minus 1 plus natural log v plus 1 minus natural log v. Remember, this c has already been taken care of in terms of the natural log a, and I did this by means of partial fraction decomposition. Some of you out there might know a better or quicker way, and you could have done it that way. But this way is a good, reliable method. It works well with me, so I'm utilizing it here. Now we're not very far away from completing this. And remember, we still have to do the substitution here at the end for v's. Let's bring everything into common logs. Natural logs in terms of sums are equal to their products. I have an ax over here in a common log. Here, sums and differences in terms of products and quotients, I'll have a v minus 1 times v plus 1 divided by v. You know that. This was in the product relationship. This right here is in a quotient with everything else, and it works out over here. Simplify this. You'll have natural log ax is equal to natural log v squared minus 1 over v. Get rid of the natural logs. They can literally cancel out by means of the properties of log. You're looking here at ax is equal to, now bring in the v substitution. V is equal to y over x. And you'll have a y squared over x squared minus 1 over y over x. The entire algebra for right here can be done right here on the side. A common denominator can be established. Here it'll be x squared. Then here you'd have y squared minus x squared. And you know this is all y over x. This y over x can come onto the other side and flip as x over y. You can erase this part right over here. When you clean out this stuff, you know this is cancelling out this square. You're really ending up with y squared minus x squared over xy. All of this right here, this specific component can substitute for everything right here. If you erase it, you can bring it right into play. Ax is equal to all of that, y squared minus x squared over xy. You can cross multiply all of this on the other side, you'll end up with ax squared y is equal to y squared minus x squared. Now for many of us, this right here is our answer, and it would be a good answer, and I would like this answer, ax squared y is equal to y squared minus x squared, the equation or the expression for which this differential equation is true. And some of you would prefer to get all the x values on one side and the y on the other side, and then you could present that as an answer, but I will stop right over here. Remember, this question now with this expression over here is solved. It represents the equation for which this differential equation is true, so it has been solved. And now utilize the partial fraction decomposition technique after arriving at this point over here. And remember, all along with what we've seen over here, this was a homogeneous equation over here, homogeneous differential equation for which we did the y equals vx substitution to help carry everything through. But that's all I wanted to show you in this particular video. It was a lengthy, comprehensive question, but it was well worth the time. Thank you for watching. Have a great day.